Hello, so today we are going to do this problem which is part of Leetcode daily challenge. Subarray product less than k. So we have an array of numbers and we have an integer k, and we want to return the number of contiguous subarrays where the product of all the elements in that subarray is less than or equal to k. So for example, this array here, how many have a product, how many subarrays have a product less than 100? Well, first is just a subarray of the individual elements. So this one, this one, this one, this one. So we have 4 right there. 10 and 5, right? This subarray is 50. The product is 50, which is less than 100. So we have here 5, 2 as well. Same thing, it's 10, so less than 100. 2, 6, and then 5 to 6. All of these subarrays, except the entire 10, 5, 2, that's not, should not be included because the product there is 100, okay? So that's roughly the idea. So when we count all of these here, it's 8, so we return that. So that's what we need to do. Now, if you look at the number of elements is 10 to the power of 4. So this tells us that we can't really do an O(n squared, because if we can do an O(n squared, we can just try every subarray and get the product and then check if it's less than 100. But we can't because that would be 10 to the power of 8, so definitely won't work for this use case. So how can we tackle it? Well, let's think about this a little bit. So whenever you have something for a contiguous subarray with some condition that is, let's say, smaller than, equal, or less than, you should immediately think about sliding window, because it's really helpful. Because with sliding window, as long as you have some heuristics by which you can decide when to increase your window size and when to decrease your window size, the conditions for these, and then you just need a way to count how many like of whatever you are looking for. In this case, we are looking for the subarrays. And so in our case here, we know that we want to increase the window if the product so far is less than k, because let's say we decrease the window. If we decrease the window, then what's the use of that? There is no real use to do that, to decreasing the window when the product is smaller than k, right? Because if you decrease the window, you will get a smaller size, but why do that? You might as well just count the entire number of windows we can get. So for example, let's say when we are at 2, how many windows we can have? 2, 5, and 2, 10. So if we decrease the window, let's say I was at 10 and decreased to 5, well, why do that? We can just count how many elements we have to the left, and that will give us how many subarrays instead of having to do it, okay? So we know that each time we want to count how many elements with ending at j at the end of the window. And so for that, we can just do j minus I plus 1. This is basically, usually this formula is for the size of an interval I to j, and that's exactly what we want. Start is I and end is j. Okay, so that's what we know that we need to do here. So this is if this is the case. And of course, we need to multiply by the product. So if this is multiplied by this one, is smaller than k, then we want to do this, but we also want to update our product. Now, this is just the current product. This would be just basically the current window product, okay? The window we are processing. Now, when do we decrease the window size? Well, usually it's the reverse of the increase window, but intuitively, why? Well, if the window is, the product is bigger than k, if we increase the window, we will only increase the product, because these are positive elements, and so they will never divide the element. They will always increase it because we multiply. And so increasing the window will only make the product bigger, right? Window will make product bigger. So we don't want to do that, because if it's bigger, it certainly won't be less than k if it was bigger than k, right? So if we increase it, we don't have a chance to be less than k if we were in the else case. So remember, here we are in the else case where p multiplied by a of g is bigger or equal to k. So increasing the window will just add more product, and so it won't give us this. And so that means we want to decrease the window in this case. And so how do we decrease the window? Well, remember, our window is going to be just I to j. And so to decrease the window, we just need to move I to the right. Okay, so we will need to increase I to the right. Now here, when we are increasing the window size, we know that we want to increase j. Here we want to increase I, right? Because let's say our I was here at 10 and our j at 2. If we need to decrease the window, our I needs to be at 5 and j stays at 2. If we want to increase the window, our j will need to move to the right. So that's why we'll have this. Now, the other thing is, when we remove 10, for example, from a product, let's say we had a product for I from 10 to 2, which is 10 multiplied by 5 multiplied by 2, 100. Now, if we move I to 5, how do we get the product of just this window? Well, we need to divide by 10 so that we remove that element. And so if we do that, then we have 10, which is the actual product of these two. And so that's what we need to do here. We need to divide before incrementing the element by the element at position I. Okay? Okay, so that's pretty much it with the sliding window. We know how to increase our window. We know how to decrease it. We know how to increment the count. And remember, the key point here with the count is that when we are here, right, when we are at 2 and our I is at j, we don't need to actually go in and count by one. We can just say this here, ending at j, will give us 3 subarrays. It will give us subarray 2. It will give us subarray 2, 5, and 2, 5, 10. Okay, so we can just count how many elements, because that's how many subarrays we will have. And since this entire thing is smaller than k, anything in between will also be smaller than k. Okay, so that's the core idea. Now, in terms of implementation, with sliding window, you can do something like both I and j are variables, and then you could just do while I is smaller than j, or while I is smaller than n and j is smaller than n. But I find this approach usually is problematic with the pointers sometimes. So what you can do is basically loop for the end or for the start. Usually for the end, it's easier in the range of the elements. And inside, so in this one, do one iteration for j. But then in a while loop, do iterations for I. Right? Because as long as we need to decrease the window, keep decreasing. So that's the approach we'll take here. Let's implement it. We'll have n, which is equal, let's just make this a, length of a. And we'll have I and j. We'll just need to initialize I to 0, but j is going to be in the range of n. And we need the current window product. Right? Now, our window product, first we will need to initialize it to 1. But then when we get to j, which means we are increasing the window size, we want to multiply by j, by the element at position j. Okay, but now we need to do the decrease the window portion. Okay, so how do we do that? We want to do it only if the multiplication, the product is bigger than k. Right, so only if window product is bigger or equal to k, then we want to decrease the window. Now, we said that to decrease the window, we need to divide by the element in position I, like this. And then as a result, we want to increment our I. But we have to be careful here. What if we kept incrementing I until I became bigger than j? That would be a problem, right? Because we need the window to be starting at I and ending at j. So we need to make sure that does not happen here. and this needs to be a while loop, because while we are bigger or equal to k, we want to keep reducing our window size. And now what we need to do here is just do the count, increment the count size for how many subarrays we will have. So here actually there is a problem, because what if I is equal to j? Now in that case we might end up with a product that is bigger than k, because if the element itself is bigger than k, then the product will still be bigger than k. So we want to do equal. And so with this, we guarantee that here we'd have a window product smaller than k. And so we can do the counting that I mentioned for the number of subarrays ending at j. So basically this is adding all subarrays ending at j. We guarantee that, we guarantee I to j, basically that the product for I to j is smaller than k. We did guarantee that by basically as long as it's bigger than k, we keep dividing and increasing I. And so we guarantee that here. And then that's pretty much it. We can return count at the end. Let's see. So this is, we need to do 0 and 1. And we need count as well. Maybe. Okay. Now if I run it, it looks like it's good. If we submit, it does pass. Now, in terms of time complexity, this entire loop will run only over in time, because even though we do a nested while loop, this here, right, will stop at I smaller or equal to j, so it will only go up to j. And so overall, this here will only go through the size of the array. So overall, the entire thing is oven. And that should pass. Yeah, that should pass without a problem. And yeah, that's pretty much the approach here. Thanks for watching.